Well, we're now ready to look at a new kind of function. Maybe you remember that I previewed this the other day, but this is going to be something that we're going to be on for quite a while. This is not just a 1 or 2 day event. There's a lot of behavior that happens in a rational function. Yet I'm trying to get you to mess around with some stuff that maybe you can do, like basically think about the number 0. The number 0 has a lot to do with rational functions, mainly because of the denominator, but as you'll find out, more than just that. But our goal is to graph this, and we're not just going to pop it in a calculator. We're going to have to analyze it, because honestly, that's part of the, you need to analyze this without a calculator, and then we will use the calculator to see what's what. So how'd you do? What happened here if you're thinking about the denominator? Did you notice that the denominator, it could be factored? Does it kind of look like it could be factored? Did you do what it wants? Did you factor it? Okay, because it makes it a heck of a lot easier to find out what makes it equal to 0 when it's in that form. So what I want to stand here before you and say is that x equals 3 is actually a bad number. The reality is we'll really say that x cannot equal 3. It's actually the same thing with -2. Again, we can say x equals -2, but the reality of this problem is x cannot equal -2 because you get a 0 in the denominator. What that means is that those two yellow numbers will become something on our graph. They'll become some type of feature. Okay? How about the numerator? Now, if you look at the numerator, it too wants to be factored. Did you let it be factored? Did you do what it wants? But really, when we think about the numerator equal to 0, what we're really doing is thinking about the whole equation equal to 0. Okay, a fraction can equal 0. It's just that the numerator is the only contribution to that. So when we say solve the equation equal to 0, solve the numerator equal to 0, we're finding some numbers that, well, that we are allowed to use. Now, x equals 1 is a number I can use. Interesting here, I thought we just got done saying that we can't use -2. We can't use -2. But now it looks like maybe I can use -2. So what's up with that? I'll fill you in a little secret. The final ultimatum is that we can't use -2. But the fact that it seems to repeat itself will also make a certain feature on our graph. Oh my gosh, plug in 0. Have you had enough of 0 yet? Well, if you plug in 0, I like to go back to the original equation, because basically you just can cover up, you can just get rid of. You're allowed to plug in 0. Make sure you process that. That just comes out to be 0 plus 0 minus 2, 0 minus 0 minus 6. So again, if I plug in 0, I actually get something. Now, what we want to do is figure out what these somethings are. And then we'll figure out if there's anything else that's even on this graph. But let's kind of talk about what these somethings are. Some of this I don't know if I expect you to know. It's okay. I'm giving you a problem that's actually a preview of a lot of this chapter. But let me just show you. Okay, starting with the last one that we did. And this one I think we can grab onto. It's something you did way back in algebra. If you plug a 0 in for x and you get the y value, you just found the y-intercept. So again, grab onto that what you already know. When you plug in 0, you get the y-intercept. So it happens to be 1, 0, 1/3. Now, again, kind of working backwards, and I know there's a lot going on here, and I'm not trying to overwhelm you, but I am showing you everything. If we go back to x equaling 1, and you remember that was to make the equation equal 0, well, that's the old adage of if you plug in a 0 for y, you get the x-intercept. That's an x-intercept because it made the equation equal 0. It made the y value equal 0. So that's nice. At least something that we've seen before. Okay, so we have an x-intercept. Now, the rest of these numbers, this is where it gets a little interesting. These are bad numbers. They're bad numbers because they made the denominator equal 0. It turns out that x equals 3 will show its ugly face by being a vertical asymptote. Well, it's not that ugly. It's a math idea, so it's got some beauty. But x equals 3 is a vertical asymptote. It represents a place that I cannot equal. Are you following me with that? It represents a line that I can't equal. What I'd like to do at this time is graph this. I know that we haven't discussed one more bad number, -2, but I want you to see how the graph behaves with these features. You're welcome to play along, or you can just watch. I will share that putting these into your calculator will become part of the package, but maybe right now you just prefer just to watch. Whenever you're ready to put it in your calculator, you always have to be sensitive to parentheses, because the way the calculator is kind of designed is it needs parentheses around the numerator and denominator to be able to represent the full fraction. Just always be careful about parentheses. All right, I'm just double checking I got that typed in right, and here we go. Again, you saw a graph like this a few days ago, but you're going to get really comfortable with this. Some things that you're going to get comfortable with are that we have branches. Now, branches would be these parts of the graph that are passing through these intercepts and also approaching the asymptote. So I have this branch over here. Notice how it's going down and approaching the asymptote, but it's not going to cross the asymptote. There's also a branch up here that seems to have some of the same behavior. That is, it's approaching the asymptote but not crossing. Remember, this is the graph of this crazy equation. Now, -2. Remember -2? It was a number that seemed to show up in two places. I told you it is bad, but yet it shows up in the numerator. If you look at the graph around -2, you don't see an asymptote. Now, what I'm doing is I'm tracing with my little spider getting close to -2. If I go exactly to -2, I'm going to go exactly to -2, you get a blank. You get a blank y value. That's the calculator's way of saying that there's no value at -2. And this is that hole in the graph that I mentioned. And again, we're going to understand. But the bottom line is there's a hole in the graph at -2. Now, there's one more thing going on with this graph. And I'll be honest with you, it's one more asymptote. But it's not a vertical asymptote. We already drew that. But there is another asymptote. And it turns out that it is horizontal. There's actually a horizontal asymptote that is also sort of dividing these branches in sort of a y value sense. In other words, that horizontal asymptote is a y value. And hopefully you sketched the graph good enough that you can throw that in there. The question, though, is where is it? Now, there's a lot of numbers on the board, and the equation itself is somewhat complicated, but I'm going to just tell you that this horizontal asymptote is at y equals 1. So that I can show you why. And it simply has to do with the connection between the numerator and denominator. Now, you guys will learn as you keep maturing in math that since the numerator's highest degree is x squared, that means that x squared will kind of dominate what this graph does as I go to infinity. When I go to infinity, I'm either going far to the left or to the right. Well, the denominator highest exponent is also x squared. And the bottom line is that these parts of the fraction, they will dominate what the graph does as numbers get really big. say it another way, I could just focus on x squared over x squared, and I could understand what's going to happen, again, far left and far right. Now, how do we get the number 1 out of this? Well, it turns out that it's the coefficients of my dominating degree. So 1 over 1 equals 1 is my horizontal asymptote. Now, I have a little more to say about that in a moment, but that gives you an idea of how we came up with y equals 1. Something you want to understand, and I'll be honest, the teacher kind of never told me, but I want you to know why things are happening in math, is that when you have a rational function, there's going to be numbers that you can't use or you can't equal. I don't know if you need to write that down, but I just want you to hear it. The reason that we have all this business going on is because there's numbers that we're not able to use or not able to equal. Okay, and simply put, that's because it's a fraction. Okay, so we have asymptotes. You saw something called a hole in the graph. Hey, kids, these are all things that you're not able to equal. Okay, and that's why they show up like this on a graph. So we end up basically, graphically speaking, we get some pretty unique stuff. Graphically speaking, we get some pretty unique stuff. I want to do one more problem a little bit in the same way, where we just kind of consider some things, and then we will put this together with some sort of solid notes. It's not going to just be a lot of random thinking. In fact, that is exactly right. When you have the same exact factor in the numerator and denominator, actually, we'll write that down as a statement in a moment, but you got it. This this rational function, which is a fraction function, is purposely a little simpler. It's funny, though, sometimes when they're simpler that we also can make them complex. That's why I want to look at this, and then we'll take some notes on exactly kind of what happens every time. 1 over x squared. Okay, now if you think about what I had you do a few moments ago, I was having you think about the denominator, because in the denominator we have bad numbers. What bad numbers do we get from the denominator? Well, it turns out we only get x equals 0. But x equals 0 is going to be a no-no, because of course that makes the denominator equal 0. Okay, now the type of no-no that it's going to be is a vertical asymptote. And honestly, the reason that it's a vertical asymptote is there's nothing else it can be, because there's not going to be a hole in this graph. So a vertical asymptote is the only feature that we cannot reach, that we cannot equal. What else did I have you do? I had you think about what makes the equation equal 0. Now, to make the equation equal 0, you kind of have to rethink where the equal sign is. In fact, what you really need to rethink is that only the numerator is going to be able to contribute to that. Okay, well, you can kind of look at that a little bit, but when in the world is 1 ever going to equal 0? What that means is that there is no y-intercept. Excuse me, there's no x-intercept. Again, simply because the equation can never equal 0. Now, speaking of the y-intercept, that was when we plugged in 0. If you want to plug in 0, you can sort of be my guest, but you should conclude that if you try to plug in 0, you get another no can do. So we get, for this problem, we get some no's. Now, there was one more thing that popped up in the problem over here. It was that horizontal asymptote. And I did an interesting thing where I talked about the degree of the numerator and denominator. For this problem, I only have a degree in the numerator represented by x to the 0. This is sometimes a little strange for kids, but degree is always the exponent on x. So x to the 0 is my highest degree. X squared is my highest degree. You'll learn that in a problem like this, we simply conclude that the bottom is bigger. Now remember what the bottom is. The bottom's a divider. And I'm sure there was a time, I think we did it in here, that if you divide by something bigger as you go to infinity, eventually you're going to divide up your piece of pie, or you're going to divide up the cookies you were handing out. You're going to divide them up to get closer and closer to 0. Okay, basically 1 divided by a big number is going to approach 0. What that means is that y equals 0 is a horizontal asymptote. I'll put that in yellow. Y equals 0 is a horizontal asymptote. Now don't worry if you got a little confused. I'm purposely just kind of telling you some stuff, but we will take some notes and make sure that you can do it. Okay, so what do we get if we graph this? Well, as you guys will learn, we get some stuff that we can feature. I can feature this vertical asymptote at x equals 0. I can feature this horizontal asymptote at y equals 0. So I can put those on my graph. And then you do go to your calculator. This actually will become part of the process, and you graph it. Okay, you graph it to basically see how it all ties together. And it turns out that it ties together with a branch here and here. Notice that both these branches are approaching the asymptotes, but of course not crossing them. I want to take some of the stuff that we said and give you guys an opportunity to kind of get it as notes, and then we'll see if we can use it one more time. Just keep in mind that this is a multi-day event. We're not going to have this all figured out in one day. But I hope that you've noticed that the vertical asymptote is going to be x equals a. Simply if a gives you a 0 in the denominator. So the vertical asymptote is going to be at x equals a. Again, simply wherever you get a 0 in the denominator. Okay, and you'll get good at that. That's actually one of the main ideas. However, there is the potential that you could have a hole in the graph. So if x equals a has a common factor, then we end up with a hole in the graph. Now, I'll share with you that this hole in the graph is something that we're going to come back to. We're actually going to spend like a whole day. We're going to spend a whole day really discussing it. But I want to show it to you today because it is part of the whole picture. Okay? So 0 in the denominator, bad numbers. They might give you a vertical asymptote. They might give you a hole in the graph. The other main thing that you were seeing today is the horizontal asymptote. Okay, now the horizontal asymptote, it sometimes looks a little crazy because there's like 3 scenarios. But for the horizontal asymptote, you will compare the numerator and denominator. And when you compare them, you're looking at the degree. And I tried to figure out a short way to write this, but basically, if the degree of the numerator is less than the degree of the denominator, if the degree of the numerator, in other words, the top is smaller than the bottom, then it will always be y equals 0. And that's what happened in the last problem we did. Again, it will always be y equals 0. However, if the degrees are equal, like the first problem we did, if the degree of the numerator is equal to the degree of the denominator, if they are equal, then you get this idea known as A over B. Now you need to understand that A over B is the coefficients. Okay, so we have this idea of the degrees are equal. We get A over B. In the example I did, it was 1 over 1. Now there's also a scenario where the degree of the top is greater than the degree of the bottom. In that case, there's no horizontal asymptote. This looks, again, kind of crazy because there's 3 rules, but it basically comes down to just comparing the top and the bottom. Now there's still the x and y intercept. Honestly, there always will be. Well, I should say there's always the chance for an x or y intercept. So good old 0. You just have to kind of keep straight. You have to keep straight how you're using the number 0. Trying to adjust to this new bell schedule. I'd like to show you a third problem. It's likely that the bell rings close to the end. Make sure you notice that the homework tonight is to do a similar thing that we're doing in class, which is to basically analyze the function for these features. And I want to kind of help you guys start to get a method to that. Honestly, the method is that students will usually list these answers, typically in the order that we presented them. So instead of it being sort of just random stuff, the first thing we do is we think about the vertical asymptote. And the good news is the vertical asymptote will always be the 0 in the denominator. So to say x equals -2, again, you just kind of say it. There's not a lot of heavy-duty math there. There's no hole in the graph because there's no common factor. We will come back to the hole in the graph in a few days, and you will feel like you're getting good at that. So I can say that you don't have to really focus on the hole much right now. The horizontal asymptote, it's the degree. Now, you should look at this problem and you should say the degree of the top is to the first. You should look at the bottom and say, oh, it's also to the first. That means we want to use A over B. A over B is going to be the coefficients. It's going to be 2 over 1. Again, it's probably something you just look at and are able to make that conclusion. Boom, y equals 2. Now, as far as the intercepts go, and this might be where I run out of time, but remember, the y-intercept is plugging a 0 into the equation. And kids get a little funny about this, but I'm allowed to plug a 0 into this equation, right? I get a 0 in the numerator and a 2 in the denominator. That means I get 0 over 2, which is the number 0. And if the y-intercept is 0, 0, the x-intercept is also. Ooh, I get some free seconds here. You want to take the time and you want to start to graph this stuff. What I just did right there was to say, hey, I know that x equals -2 and y equals 2 are asymptotes. See how I drew them? 0, 0 is an intercept, so I know that. The only thing left to do is to get out my calculator and see how it all goes together. Okay, and you see how it all goes together when you get out your calculator and you see a branch right here, and you see a branch right here. Eventually, we'll learn how to graph them without the calculator, but that's also down the road. This is an important homework assignment. It's important because it's the first one. I don't want you to get frustrated if maybe there's something that pops up that's a little tricky. It's part of your growth, but I do hope that you look at the homework with some intensity, and we'll pick it up tomorrow.